Alright, this video is about Chapter 9. In Chapter 9, we're only going to cover the first 3 sections, or the first 4. So, Chapter 9 is building on what we did in Chapter 8. In Chapter 8, we learned how to do Lewis structures. And in Chapter 9, we're going to apply a new theory called VSEPR for short, and it means valence shell electron pair repulsion theory. And we apply the theory to a Lewis structure, and it will help us determine the 3-dimensional geometry of that structure, or that molecule, or that compound. So it works really well, and you notice that Lewis dots are really easy to work with, and now we're going to be able, just from the Lewis structure, determine the 3-dimensional geometry of the molecule. So in section 1, we're going to determine, we're going to talk about what is molecular geometry, what are some of the basic shapes. Then we're going to do molecular geometry and polarity in section 2. That's a really important chapter. I can't stress enough molecular geometry and polarity. So here we're not talking about bond polarity. We're going to be talking about molecular polarity, the polarity of the entire molecule. And section 2 is the most important to master to be able to do the next chapter we cover, which is chapter 11. So I can't stress enough that you really need to focus on section 2. I find that the students who struggle with this section, it's because they really haven't gotten down electronegativity in chapter 8. So think about that. Chapter 8, make sure you understand electronegativity differences, bond polarity, and dipole moment. That's what's required to be successful in section 2. Section 3, we've kind of talked about this. I'm going to talk just a little bit about it, and that is, optimum overlap to create the electron shared pair, which is the valence bond. And then in section 4, we're going to do hybridization of orbitals. It's just a quick, easy way of talking about when we look at water, you're going to see that water doesn't, the hydrogens that are attached to the oxygen are not 90 degrees from each other, which is what you would expect if the p orbitals are either on the x or y or z axis. They're all 90 degrees from each other. So we're going to find out why, what theory helps us explain the true angle between the hydrogens in water. And then we're not covering sections 9.5, 9.6, or 9.7. All right, so VSEPR model, electron domain geometry. Make sure you understand that, electron domain geometry. A lot of students forget that one because we are going to focus mostly on molecular geometry, but in order to get the proper overall structure, you have to know the electron domain geometry. And then deviations from ideal bond angles, and then the geometry of molecules with more than one central atom. Alright, so valence shell electron pair repulsion theory is the model that we use to determine the 3-dimensional geometry of covalently bound compounds. And it does a really good job. For as simple as this theory is, it does a very good job. And what this theory does is it says, it gives a hierarchy to electron pairs that repel each other. So we know electrons or like charges repel each other. So pairs of electrons will repel each other. The most repulsive of the electron pairs is the lone pairs. The lone pairs that are not bonded to another element, they're only assigned to one atom, they have the most repulsion. So lone pairs have the most repulsion, and then we'll have single bond, double bonds, and triple bonds. So as far as electron pairs go, or as far as a VSEPR goes, though, it does not distinguish between the single, double, or triple bond. They just consider that one group. All right. So we have bonding groups, non-bonding groups. Non-bonding groups are more repulsive than bonding groups. All right, so let's look at the model here. So we have carbon dioxide and we have ozone and we have ammonia. And so in the valence shell electron pair repulsion model, let me see if I can, all right, we look at the central atom. That's what we focus on. We focus on the central atom. And then on the central atom, we look at what types of groups are coming off of this atom. So we have a double bond here that we learned how to do in Chapter 8. And we have a double bond here that we learned how to do in Chapter 8. And this is the proper Lewis structure for carbon dioxide. Everything has 8. And we have a total of 18 electrons, or let's see, is it 18? It's 16 electrons. So that's what we have. So in VSEPR theory, it doesn't distinguish between a double bond or a single bond or a triple bond. So this is what I like to do, and this isn't really stressed in the book, but to me this is important. Make A stand for the central atom in general, and then the electron domains coming off of the central atom, we call those bonding groups. And so we would give this an electron domain of AX2, or a category, let's say this, categorization of this molecule is AX2. So again, A stands for the central atom carbon, and X stands for the two bonding groups coming off the central atom, and this is called AX2. And you go, why do I need to do this? Well, the next question is, how do you keep two things as far away from each other as possible? Well, you put an X on this side and an X on this side. And now you have the geometry and shape of carbon dioxide. It's linear. So that's where we're going with this. So we now know that the geometry or shape of this molecule is linear. Now, some books don't use an X here. They say AB2 for bonding groups. And so don't get those, don't get hung up on that. Some books say AB2, some books say AX2. Doesn't matter. All right, let's look at the ozone. So ozone's a little different. You got an A, which is the central atom oxygen here. But on this you have two bonding groups, AX2, but we have something different here. We've got a non-bonding pair. So to symbolize the non-bonding pair, we put a E there. E stands for lone pair, or lone pair group, if you want to think of it that way. And you go, well, why is that such a big deal? Well, instead of having two things coming off the central atom like we see with carbon dioxide, we have a total of 3 things coming off the central atom. So how do you keep 3 things as far away from each other as possible? Well, you put them in the corners of a triangle. So here's the central oxygen. There's a lone pair in this corner. There's an oxygen in this corner, and there's an oxygen in this corner. There's a double bond to this one, single bond to that one, and then for the lone pair we put a balloon like this. Now what the balloon represents is it represents repulsion and space that the electron pair takes up. So notice this electron pair is a lot more repulsive. It's not being shared with another positive nucleus, and so it takes up so much space it forces these bonding groups, this bonding group here and this bonding group here, closer together. So it actually has the non-bonding pair has so much force it forces the bonding group together. Now, if there wasn't this additional force, what I would expect you to be able to do is tell me what the angle is between this oxygen, and this oxygen. All right? And you would say, okay, if there was no force from the non-bonding pair, you would say the angle is 120 degrees. And you go, some people are saying, how'd you get that? Well, here's a circle, right? This is the full circle. And in a full circle, 120 times 3 gives you 360. So in a perfect, where these lines are perfectly divided in a circle, that would be 120, this would be 120, and this would be 120. But because of the lone pair forcing the bonding pair closer together, your answer for this would be less than 120 degrees. So that's a less than sign. Less than 120 degrees. Okay? So that's another way we would symbolize it. All right, let's look at another one here. So this one, you would have A is the central atom, nitrogen. You notice there are 3 bonding groups coming off the central atom, so that's AX3. And then you have another lone pair right here, E. Now this is the hardest one of these 3 to figure out. So my question is, what would be the 3-dimensional geometry of this, of ammonia? So what I want you to do is, I want you to think about how do you keep 4 things as far away from each other as possible? How do you keep 4 things as far away from each other as possible? And stop the video and try to draw it yourself. How would you keep 4 things as far away from each other as possible? Stop the video, and then when you've got your structure, you can click it back on, and you can see if you got the right answer. All right. So what most people do that haven't had VSEPR, they say, well, that's easy. I'll have it just like this picture. Everything's 90 degrees from one another. So 90 degrees here, 90 degrees here, 90 degrees here, 90 degrees here. So 90 degrees. That's what you would say. Is there a way to do the geometry and get better than 90 degrees? Absolutely. So here's how it works. You got to think in 3 dimensions. So we still have the lone pair here, and we have a big balloon here to represent that it's a lone pair, non-bonding pair. We use a solid line here to say that this hydrogen is in the same plane as the board or the screen that you're looking at this on. So solid line means in the same plane. So this hydrogen and nitrogen are in the same plane. Now, another hydrogen is coming out of the board at you. And to show that it's coming out at you, we use a triangle. You can fill it in if you want to, but you don't have to. And then there's another hydrogen that's going back behind the screen. And you would put that as a dashed line. And some people get fancy here and use a dashed triangle. You can do that too. Either way, dashed line or dashed triangle. So you're probably looking at this and going, well, what's that angle? Well, if this wasn't a lone pair on the ammonia, the angle would be 107 degrees. No. If there was no lone pair, it would be 109.5 degrees. It'd be 109.5 in a perfect four attachments to the central atom system. But because of the lone pair repulsing the bonding pairs on the hydrogen and nitrogen, the angle is actually 107 degrees. All right. So let me do one where it's perfect. If you had CH4, all right, CH4. I'll just CH4. Then you would have carbon in the center. You would have a hydrogen here. You'd have a hydrogen here. Notice these are both solid lines. That means in the same plane as the screen. You'd have a hydrogen coming out at you, and you'd have a hydrogen going back through the board. So that's the dashed line. So in this case, that's a perfect geometry. No non-bonding pairs. It's AX4. No non-bonding pairs, just bonding pairs only. And then the angle between the hydrogen, and the way we do this is angle between hydrogen, carbon, hydrogen equals 109.5 degrees. All right? Angle between the hydrogens are 109.5. And so it'd be 109 there, it'd be 109.5 here, 109.5 here, 109.5 here, and then back behind here, 109.5. So, and then 109.5 coming down this way. So everything's 109.5. So your book stresses electron domains. That's what these are called. This is 2 electron domains. This is 3 electron domains. This is 4 electron domains. And then we can break the domains down. It's all bonding here. Doesn't matter whether it's single, double, triple bond, that's one group. So there are two bonding electron domains. For the ozone, you have 2 bonding electron domains and a non-bonding electron domain. And you go, why is that important? Well, you've got 3 things coming off the central atoms. That's what determines that the geometry is going to be this, which is called, as if it was all AX3, it'd be called Trigonal Planar. But because we treat the lone pairs invisible here, we just look at this part. We say that the shape or geometry is bent. All right. So always treat the lone pairs like they're invisible. So this lone pair on ammonia would be invisible. So if you want to describe this part down here, you would call it Trigonal Pyramidal, because it's got a base of these 3 hydrogens, and then above the base is this nitrogen, and so we would call it Trigonal Pyramidal for the geometry, or molecular geometry. So maybe that's a good point to stress here, is that excuse me, if it's nothing but bonding pairs coming off the central atom, the electron domain geometry and the molecular geometry are the same, which is linear. All right? The electron domain, which is 2 electron domains coming off the central atom, the electron domain and the molecular geometry are the same. They're linear. Now, let's compare that to this ozone. In the ozone, we have 3 things coming off the central atom. So the electron domain for this is called Trigonal Planar, flat. That's what the electron domain is. But the geometry is, let's do this. Let's see if I can do this, and that'll make it look a little neater. The geometry is, and it's not going to let me erase over here. Let's see. Nope. The geometry is like this is invisible here. And so all you see is this part here. And so the molecular geometry is bent or angular. Bent or angular is another name for it. Or I've also heard it called nonlinear. Let's do that. Nonlinear. I like angular bent better. Nonlinear, not so much. All right. And the reason why you have a different electron domain geometry than a molecular geometry is because you have this non-bonding pair, lone pair. And the lone pair is invisible. So you can only see this part on the molecular geometry, but you see the whole structure when you do electron domain. All right, let's look at this last one. So here, you got a total of 4 electron domains. So the question is, how do you keep 4 things away from each other as far as possible? It is not flat. It's not this, because the angles are all 90 degrees. So it's this geometry. So the electron domain geometry for this is called tetrahedral. Tetrahedral. Oops, it's an E there. Hedral. Means 4-sided. You say, how do you get 4 sides? Well, you got a side here. You've got a side here. You got a side behind. You got a side underneath. That's how they get tetrahedral. So the electron domain for ammonia is tetrahedral. But the molecular geometry is what you see only with the bonding pairs, and that's called Trigonal Pyramidal. And if you're not sold on my writing here, you will see it in a list here in a minute. All right, Trigonal Pyramidal. So I think it's funny. There's a lot of information on this slide. You've just seen valence shell electron pair repulsion theory in a nutshell. It's all right here. We do Lewis structure. We evaluate the Lewis structure. A stands for the central atom, and X or B stands for the bonding groups coming off the central atom. I'm going to use X's. And then if there's a lone pair coming off the central atom, you use the symbol E. That's the lone pair. And then the question is, how do you keep these electron pairs as far away from each other as possible? And knowing that lone pairs are more repulsive, highly repulsive compared to bonding pairs. So if you keep that all in mind, which is a lot, it is a lot, but if you keep it all in mind, you can then progress to molecular polarity. All right, so let's do some more. So this one here, you start off with this. Now you should know the name of this. This is phosphorus pentachloride. Penta means 5. We learned that in chapter 2 on naming. And if some of you are watching this before our midterm exam, this is worth watching to help you with the midterm exam. Because here it is. You keep asking, like, why would you ever use a Lewis structure? Well, here it is. Here's the Lewis structure for phosphorus pentachloride. You went 5 valence electrons here, and you said 5 times the 7 valence electrons for each chlorine. You add that up, you got 40 electrons, and there's 8 electrons around each one of these chlorines, and so 8 times 5 is 40. So there's all of your electrons. Now, you know this isn't going to follow the octet rule. It's going to have an expanded octet, and you know it's an expanded octet because you have 5 bonds coming off the central atom. So 5 bonds coming off the central atom says that we're dealing with an expanded octet. So what you need to do then is you would think about what's the classification. And again, I don't think the book stresses this enough, but to me, one of the most important parts of this is to classify this. This is AX5, where X stands for these bonding groups, the 5 bonding groups coming off the central atom. Again, VSEPR does not distinguish between a single, double, and triple bond. So AX5, the electron domain geometry, EDG for short, and the molecular geometry are the same. And the name for this geometry is called Trigonal Bipyramidal. Trigonal Bipyramidal. You said, what does that mean? Well, trigonal means 3, pyramidal means pyramid. All right, so let me change the color here. Let's change it to red maybe so that you can see this. Maybe this dark red. I think it's contrasting. So what you have here is these 3, I didn't change that to red. These 3 are in the same plane. This chlorine is above the plane. There's my pyramid, and it's 3-sided. And this pyramid is below the plane. So that's what happened, is that there's a pyramid, a 3-sided pyramid above the plane, 3-sided pyramid below the plane. So the way I actually draw this, if I was drawing it for class, is I would say, okay, you put the phosphorus here, you put a solid line up here like this and put a chlorine on it, and you put a solid line down here and put a chlorine on it. And let me just say, this is called the axial position. These vertical ones here are called axial. They are actually longer than the ones that come off of the phosphorus in the same plane down here. So these 3 are in the same plane. This is a triangle here. It's kind of like the equator. It separates these 3 here. All right. And so actually, it's okay. I should have put this out like that then and make this the like. There's no way to erase that. Let me see. Oh, yeah, there's up here. Let me do this. Let me erase this. Yeah, I can erase this too. I just found out. All right. So let me change the color. Let's see. Is this going to change it? Yeah. So you can see it's a 3-sided pyramid right there. All right. That one goes up there like that. 3-sided pyramid. So the same thing here. you put the phosphorus here, and then you have one coming out just straight out like this, and that's phosphorus. Then you have one coming out like this out of the board, which is like a triangle. And then you got one going back in here behind the board, behind the screen, looks like that. And there's my three-sided pyramid right there. All right. So I just want to say the axial bonds are longer. The equatorial bonds, that's these in the equator here, they're actually shorter. They are actually shorter, and that's going to have some implication later on. Shorter. All right. So for this last one, what I would tell you to do is, you might want to stop the video and just write this and see if you can do the Lewis structure for it. Because what you should do is, let's stop the video. Click stop. Try it out yourself, and then come back. All right. So you're back, and you say, okay, xenon has 8 valence electrons, and fluorine has there's 4 of them, and each one has 7 valence electrons. If you add that all together, you got 36 electrons. 36. And we'll go with the bigger, wider one. All right, 36. So you put 8 around here. You know that each fluorine has to have 8. And it has 8 because remember that line there is a shared pair. So there's 32. Where do you put the extra electrons? Well, we learned in Chapter 8, any extra electrons, these are non-bonding pairs or lone pairs, are assigned to the central atom. So any extra electrons that you have should always be assigned to the central atom. So this one would be AX4E2. 6 things coming off the central atom. How do you keep 6 things as far away as possible around a central atom? So watch this. You'd have xenon. Back behind the board, you would have a fluorine. And back behind the board on this side, you'd have a fluorine. And then you would have a fluorine coming out of the board with a triangle. Fluorine coming out of the board like a triangle. And then you'd have a lone pair above the plane and a lone pair below the plane. So the electron domain geometry for this is called octahedral. Hedral means sided, octahedral. But the molecular geometry would be square planar. And so all you that said the methane would be 90 degrees between each hydrogen, the only way you get 90 degrees between something like that all the way around is if it's square planar. So all these fluorines here are in the same plane. They're in the equatorial position, and it's 90 degrees between each of them. Now, the thing about octahedral is the length of all the bonds are the same. So it's not like this one, the Trigonal Bipyramidal, where the axials are longer than the equatorial ones, the ones on the equator. In an octahedral electron domain, all bonds are the same length. So you can rotate this around. You can't really tell top from bottom or side to side. All right, so notice again what we did. We took the Lewis structure, we drew the Lewis structure, we've got the correct Lewis structure, and then we determined the classification. AX4, there are 4 bonding pairs coming off the central atom, and then 2 non-bonding groups, that's the E2. And then what you want to do here is get some flashcards and memorize electron domain geometry and what's the molecular geometry or shape of that molecule or compound. So when it's AX4E2, the electron domain geometry is octahedral. That's what tells me the framework. And then what I see with the eye is where the bonding groups are, and that's called square planar, and you're done. And then we're going to add one more thing to this chapter, and that is electronegativity or dipole moment or bond polarity. Totally, it's called, in the end, we're going to look at bond polarity. So the next thing to look at is what do these shapes look like? Is there a way to show the shape? So here, this would be like carbon dioxide. You got carbon here, double bonded here to the oxygen, double bonded here. Notice I'm not interested in the lone pairs on the oxygen. We are only focused on the central atom. So for this one, this would be AX2. Remember, single bond, double bond, or triple bond is just one group coming off each side. And so how do you keep two groups that are the same charge happy? You keep them as far away from each other as possible. And so that's how we get the linear geometry here, linear geometry of carbon dioxide. Now here, this would be like sulfur trioxide. Maybe you have a double bond on this oxygen and a single bond on this one and a single bond on this one. It doesn't matter whether it's a single, double, or triple. That's one domain. This is the other electron domain. This is the other electron domain. This would be AX3. How do you keep three things as far away from each other as possible? You put them in the corners of a triangle, and that's what they are showing here with these balloons. They're in the corners of a triangle. All right. So the next one, really the next one in the progression is this one. It's this one. So what happens here is you have maybe a carbon here and a hydrogen here and a hydrogen here and a hydrogen here and a hydrogen here. And notice that doesn't look anything like what we've been doing, where we would say these hydrogens are attached right on the axis. They would be 90 degrees from each other, but you can see these hydrogens aren't 90 degrees from each other. In fact, from here to here, back through here to this hydrogen, that angle there is 109.5 degrees. So this is not the structure. To think three-dimensionally, you're going to have a hydrogen here, a hydrogen here. These are all in the same plane. So you're telling me which ones are in the same plane? Yeah, this one's kind of tough because they've got them twisted a little bit, so none of them are in the same plane. But by convention, you would rotate this balloon here till, by convention, one side's flat, and that would be the two hydrogens and the carbon. And then when you rotate it like that, you'd have one coming out of the screen, and you would have one going back through the screen like that. And you use a dashed line to represent that. So this geometry is tetrahedral, and again the angle is 109.5 degrees between the hydrogen, carbon, hydrogen. Over here we got this would be like sulfur hexafluoride, where there's a fluorine here, fluorine here, fluorine here, fluorine here bonded, fluorine here, and a fluorine here. Yeah, you can't see these too well here, but all right. So this would be like sulfur hexafluoride. So the EDG, the electron domain geometry, and the molecular geometry are the same for but all of these. This one would be octahedral. This one would be trigonal bipyramidal. And this last one would be tetrahedral. All right. Now let's talk about angles. Between the angle between the sulfur, fluorine, axial, sulfur equals 90 degrees. That would be here to here to here. That's an axial. All right. What about angle between, oops, I did this wrong. No, yeah, I did. This is, yeah, let's erase that. All right, let's do that over. Just realized I didn't do that right. All right, so the angle between, yeah, I didn't need to erase that much, but we can do that. The angle between the fluorine, sulfur, fluorine, and these are, this would be equatorial, this would be axial. So this is the equatorial one, and this would be the axial. That angle is equal to 90 degrees. All right. You could have angle between fluorine axial, sulfur and fluorine axial, the other one, so it'd be from here to here, and you'd say 180 degrees. And you could do fluorine, angle between fluorine equatorial, that's the central atom, and then fluorine equatorial, that would be 90 degrees. So the two angles that describe this geometry are 90 and 180. For the trigonal bipyramidal, the equatorial here is 120 degrees between each bonding group here, like this. What is this one again? This, we said, phosphorus pentachloride. All right, so that's the equatorial, and then we have axial here, and we have an axial down here, and the axials are longer bonds than the equatorial. And then the last one here, this is just again, tetrahedral is the way you keep four things as far away from each other as possible. So the angle, let me do that. The angle for the trigonal bipyramidal, it's 120 degrees between these on the equatorial positions, and then from the equatorial to the axial, that's 90 degrees. 90. Okay, that makes sense. And then for the tetrahedral, they're all 109.5. Doesn't matter how you slice it, from one hydrogen to the other hydrogen, and ammonia. Well, this is not, I didn't do ammonia. This is methane. Yeah, methane, to see there. So the angle between hydrogen, carbon, and hydrogen and methane is 109.5 degrees. All right? We're going to get more practice, but you should start to see the pattern and see a foundation here. All right, so this is it. These are your basic geometries that we're covering in class this semester. The simplest is linear, 180 degrees. You're keeping the bonding pairs here as far away from each other as possible. To keep three things away from each other as possible, we put them in the corners of a triangle. And now you can see with the green arrows here, that total degrees is 360. So it's 120 degrees here, 120 degrees here, 120 degrees here. So the electron domain geometry and the molecular geometry are the same for all of these as far as when we classify them. So for trigonal planar, this is the trigonal planar electron domain geometry, and it's the trigonal planar molecular geometry. Over here, this linear, it's electron domain geometry of linear. It's also a molecular geometry of linear. All right, so here's our tetrahedral we just did, and remember the angle is 109.5 degrees. 109.5 anywhere in the molecule. All right. Trigonal bipyramidal, notice they use different colors here. They tell you that this one's 120, and they tell you that one's 90. All right. This one, they describe it all by 90 degree angles. They don't even do the 180, like from here to here. They just say everything's 90. But the axial, what's not right here, the axial, we'll just say, let's see what we want to call it, variable y. Variable y here and variable y here. So if you do y axial through the central atom, we'll call it blue, and then y axial again, that's how you get 180 degrees from here all the way down to here. All right, so notice all of these. This would be AX2 for both the electron domain and geometry. This one would be AX3. This one would be AX4. This one would be AX5. And then the last one here would be AX6. So when they're all bonding, all you're going to have is A, and then the number of bonding groups coming off the central atom. All right, so they're stressing again, you need to know the electron domain geometry and the molecular geometry. So here's the ozone we've been working with, and we said that it's the electron domain geometry is what you can see in terms of bonding groups and non-bonding groups. So here's why I like this part. If you go AX2E, you see there's three things coming off the central atom. This is our central atom right here, oxygen. So you got a bonding group here, or an X, and I'll call it a bonding group here, and a bonding group here, and then the non-bonding group here, which we symbolize with the balloon like this. Highly repulsive. So the electron domain geometry takes into the non-bonding or lone pairs and the bonding pairs. The molecular geometry assumes the lone pair is invisible, so we only see this part. And so that molecular geometry in this book is called bent. It could also be called nonlinear or angular. And then the angle here, don't get suckered into thinking this is going to be 120 degrees. When you see this lone pair here, you know it's forcing these two closer together. So you would say less than 120 degrees. All right. So here's a table that you need to memorize, and that is, you need to memorize, to me what you need to memorize is the classification and the electron domain geometry and the molecular geometry. Now, this is a little confusing to me. They say the type of molecule is AB2. But they're not taking into account the non-bonding pairs. So when we look at this, I would call this AX2E. There's three things coming off of it. There's a total of three things. So the electron domain geometry, because there's three things coming off of it, is trigonal planar. Because this lone pair is invisible, we don't think of it when we do the molecular geometry, based molecular geometries on what we see, then the molecular geometry is bent. And that's what you should get out of it. All right, we'll do another one. This one here, I would classify as A, X, 2, or 3, E. So there's a total of four things coming off the central atom. There's the three bonds, and then there's a lone pair here, and I'm just going to put a balloon there. So the electron domain geometry is tetrahedral. If you have four things coming off the central atom, the geometry is tetrahedral. But the lone pair is invisible up here. It does force the bonding pair closer together. So this is what we see. This is the lone pair is invisible. And so this is called trigonal because it's three sides, 1, 2, and the one in the back here. Pyramidal, because it comes to a peak here. So the molecular geometry for this substance, like ammonia, is the molecular geometry is trigonal pyramidal, but the electron domain framework or electron domain geometry is tetrahedral. So if you don't get the electron domain geometry correct, you have no shot at the molecular geometry. And what I see on a test a lot is students write the molecular geometry, but they don't take into account the lone pairs, and that causes problems. So here we've got AB2, E2. So here you can see it. This is AX2, E2. So you know there's four things coming off the central atom. If there's four things coming off the central atom, the electron domain geometry is tetrahedral. Now what's strange about this one, you got a lone pair here, and you got a lone pair here. If those are invisible, all we see is this part. And so we would say this molecular geometry is bent. Now let's talk about the angle here. There are actually two lone pairs. There's one here, there's one here. They force these two bonding pairs so close together in water that the angle is 104.5 degrees. So in water, that's what the angle is between the two hydrogens. So the angle between the hydrogen, oxygen, hydrogen in water would be 104.5. Why 104.5? Because the two lone pairs force the bonding pairs closer together. If it was a true tetrahedral geometry, it'd be 109.5. We lose 5 degrees because the lone pairs are so repulsive, they push the bonding pair closer together. And that's what you should get out of that. All right, here's some more. So you look at this structure over here. If it's all bonding pairs, it is AB5, and that would be the electron domain and the molecular geometry. But what we have over here, it's called AB4E. So there's 4 bonding groups, and you can see them, 4 bonding groups, and then there's a non-bonding pair right there. So the non-bonding pair actually forces these bonding pairs a little back like this. All right, they get distorted. Non-bonding pairs repel all other electrons. So when it's AB4, it's got 5 things coming off the central atom. So you'd say the electron domain geometry is Trigonal Bipyramidal. But what you see with the eye, let's draw this up here and flip it on its side. You see like a sulfur in the middle here, and a fluorine on this end, and a fluorine on this end, and then coming out at you is a fluorine, and going back through the board is a fluorine. Well, we call that seesaw shape, because it looks like a seesaw. This side could go up, that side could go down. So it's a seesaw shape, and there's the fulcrum right there. All right, so that's how we get that. And then we have, notice these are all the same type. These all have the same electron domain geometries. This one is called AB3E2. So it's still 5 things coming off the central atom. And I've gone from B's, X's to B's. I will use them interchangeably. All right. So we have these 3 bonding pairs here. And then we, instead of having, well, we start off with that. Let's say we do, let's erase that. We start off with, the possibility of having trigonal bipyramidal because there's 5 things coming off. But when we look over here, we have 2 lone pairs. We have a lone pair here and a lone pair here. Now, let me just say, this is the really important thing about trigonal bipyramidal. In trigonal bipyramidal, the lone pairs always go in the equatorial position, always. So here we had 1 electron pair. Let's erase this back up here. And so this is AB4E. And again, notice the lone pair is on the equatorial position. Then we go to AB3E2. Notice both of the lone pairs are on the equatorial position. And then the last one we have here is B2E3. Still 5 things coming off the central atom. Still has the electron domain geometry of trigonal bipyramidal. But over here, you can't see these lone pairs. You can't see these lone pairs. So all you see is this vertical line here. And so you would say it's linear. And the example they give is IF2 negative. So you may want to try these out on your own. Just, this is what you might want to do. You might want to stop and write these down over here on the right. And then try making the correct Lewis structure. And if you get the correct Lewis structure, then you can do the classification. And if you get the classification, the electron domain geometry, then you can figure out the molecular geometry, and you're done for this part. All right, let's look at the next slide. All right, and this is the last of the geometries that you have to know. So this one would be AX5E. Got a lone pair here. And this one here would be, we just did it, AX4E2. So there's a total of 6 things coming off the central atom. So both of these substances are octahedral in shape. So they have octahedral geometries, or electron domain geometries. But over here, this lone pair is invisible, so we have to describe it based on the lone pair actually forces these bonding pairs upward towards the oxygen, and we call this square pyramidal. Square pyramidal. You can see if I erase that, it looks like a square pyramid. So let's do that. Let's do it right here. Yeah. So you can see that square pyramidal, or pyramidal, if you want to say that. But what you notice is that the geometry that gives rise to square pyramidal is AX5E. All right, when we go to knock another bonding pair off, it is going to be this pair. Why? Because this is the lone pair. It's highly repulsive. It actually forces these bonds up a little bit. And then it can push this electron completely away since it's electronegative, and it's since these electrons are non-bonding, and then you want to keep the non-bonding pairs far away from each other as possible. So this becomes a lone pair here. You wouldn't want to put them 90 degrees from each other is what I'm trying to say. So that's why we get this square planar. The lone pair's here, and the other lone pair has to be 180 degrees from it. That's the only way you get a square planar geometry. All right. And that's it for the geometries. So now what you're tasked to do is to follow these steps and be able to write the molecular, three-dimensional molecular geometry for anything given to you that's a covalent or molecular compound. Now, the key is, and this is what students just they don't get all the time, this is the most important. You've got to find the electron domain geometry first, and it's important, but the most important is getting the correct molecular geometry. But in order to get the correct molecular geometry, you must first get the electron domain geometry. And I find students, that's what causes problems. They try to go directly to the molecular geometry without going through the electron domain geometry, and they inevitably get the wrong answer. All right, so this is the type of problems you could expect on the next exam. So we learned in Chapter 8, in fact we did this one in class, sulfur trioxide, and here we have iodine tetrachloride ion. And so we know how to do this part. Now, if you don't know how to get the correct Lewis structure, you've got to go back to Chapter 8 and you've got to look at it, because if you cannot do the Lewis structure, the proper Lewis structure, there's no way you're going to get the geometry right. So when we did this problem in class, we know that there's resonance. Resonance is where you can draw more than one correct Lewis structure. So the double bond could be on the central oxygen, or the double bond could be on the right-handed side oxygen. I'm not going to do the full Lewis structure. I just want to show that that's what you get, resonance. You do get resonance between these three structures. Now, here's what's cool. I don't care which one of these resonance structures you choose here. They're all AX3. Bonding group, bonding group, bonding group off the central atom. Bonding group, bonding group, bonding group off the central atom. Bonding group, bonding group, bonding group off the central atom. Again, VSEPR does not distinguish between a single, double, or triple bond. They're all just one group. There's three groups coming off the central atom. How do you keep three things as far away from each other as possible? You put them in the corners of a triangle like this. All right? And so the molecular geometry and the electron domain geometry will be the same, since there's no non-bonding electrons on the central atom. And what is the name for this one? Trigonal planar. It's flat. Trigonal planar. All right, let's look at this one. we know iodine doesn't have to follow the octet rule. We would label this as AX4, and then we got a non-bonding group and a non-bonding group, so it's 2 lone pair. So we would say AX4E2. So we have a total of 6 things coming off the central atom. How do you keep 6 things as far away from each other as possible? Well, put the iodine here, you put a lone pair here, and you put a lone pair here. They need to be as far away from each other as possible. And that's going to force a chlorine to pop out of the board like this. And it's going to force a chlorine to pop out of the board like that. And then back behind the board on the same equator is the other chlorine. So the EDG, electron domain geometry, is octahedral. And the molecular geometry is what you see with only the bonding groups. And so you see the 4 bonding groups where the chlorines, these 4 bonding groups, 1, 2, 3, 4. If you only have 4 bonding groups and 2 lone pairs on the central atom, then the molecular geometry becomes square planar. Square planar. And that's what we see here. This is a square here. And then you have a lone pair above and a lone pair below the plane like that. That's the only way you get square planar. AX4E2 for the electron domain geometry. All right. Let's look at the next one. There's what it looks like. So, I don't like the way the book does this. I wish they would just, I mean, this one's okay because it's the same. This is AX3, right? AX3, AX3. These are the actual colors. Oxygen for is red and yellow for sulfur. And you can easily see when you look at this that the molecular geometry and the electron domain geometry are the same. They're both trigonal planar. Flat plane, flat triangle. All right. Next one. This one we've done too. So electron domain, this is a lone pair here, and this is a lone pair here. So it's really AX4E2. And when you see 6 things, it's always octahedral for the electron domain. And this is the way we would draw it. And I would put a big bubble here, and I'd put a big bubble right here. Lone pairs are highly repulsive. So that keeps these in the same plane over here. And so the molecular geometry is square planar. So you go, well, why don't we just go directly to the molecular geometry? Well, you got to get the framework first. You got to know it's octahedral for the framework here before you can start. You take off some bonding pairs and put non-bonding pairs here. They have to be 180 degrees from each other, which lends itself to that molecular geometry. So you got to get the electron domain geometry first. Don't rush it. Get it first, based off the Lewis structure. That's how we knew it was. There's bonding group, bonding group, bonding group, bonding group, and then a non-bonding and a non-bonding group. So that's how we get 4 bonding groups, 2 non-bonding groups, or 2 lone pairs. Once we get that, we can get the electron domain geometry, put in the electron pairs. No, they need to be as far away from each other as possible, the non-bonding pairs, and we end up with molecular geometry of square planar. So what I think you should memorize that helps is memorize the classification and know what that shape looks like. Know what that shape looks like as far as electron domain goes and what molecular geometry looks like. All right, I like this slide, and I want you to look at it and focus on it because it's got a lot of implications, and I find students kind of gloss over this slide, and it's really important. It's going to become even more important in the next chapter or the end of this chapter. So you look at ammonia, and you know ammonia has a lone pair right here. How do you know that? Well, this is 5 valence electrons plus 3 times 1. That's a total of 8 valence electrons. There's 2 right there. There's 2 right there. And there's 2 right there. So we have a lone pair here, which is a balloon here. Well, in a normal normal tetrahedral, you know the angle between hydrogen, nitrogen, and hydrogen would be equal to 109.5 degrees. But this isn't normal. This isn't AX4. This is AX3E. So the E is highly repulsive. That's why we make a big balloon around it. And it forces the bonding pairs closer together. How much? Well, the angle between the hydrogens in ammonia is 107 degrees. I would say if you're, you may want to memorize that one. I'm more interested in the angle between water. So this is the one I'm most interested in. The angle in water, because of the 2 lone pairs here and here, force this angle to be 104.5. That one I definitely want you to know, 104.5 degrees. All right, so then we have our favorite formaldehyde, and we did the Lewis structure for it, and you would say that the classification for this is AX3. That's one bonding group, that's another bonding group, and this double bond is a bonding group. So how do you keep 3 things as far away from each other as possible? Well, you put them in the course of a triangle. But because there's a double bond on this oxygen here, it has a little bit more repulsive force, and it forces the 2 hydrogens together by 4 degrees. So for this one, the molecular geometry and the electron domain geometry are the same. There's no non-bonding pairs on the central atom. So we would say this is trigonal, means triangle. That's the adjective. And then we would say planar, trigonal planar, flat triangle. That's what you're saying there when you say trigonal planar. All right. This next one, they don't show, but there's a lone pair here, and you can do the Lewis structure yourself to prove that there's a lone pair right here. The lone pair is super repulsive, so it blows back this fluorine and this fluorine, and it causes these 2 fluorines to get closer together. So we know in a true tetrahedral, this angle here should be 120 degrees, and this one's been pushed to 101.5. We know that if there wasn't any blowback here, this angle here would be 90 degrees, and it's not. That angle is, they actually don't even show it. They actually combine this one with this one to show you that that angle would be then 90 and 90 would be 180 degrees if you did all of that, 180. But it actually comes out to be 173.1 because it forces these axial backwards, doesn't take as much distance to, it forces those back. So therefore, it reduces the angle between the axial fluorine here and the equatorial fluorine there. Maybe I better clean that up. Let's do that. All right, so let's change that. So you got the 2 lone pair here. They're not showing. And it forces these backwards, which reduces this angle here. Now, I'd like to, I think it's funny they don't say less than 90. So they're comparing just axial to axial and equatorial to equatorial here. And that's okay, but, there's different angles here. This one here between fluorine axial, sulfur, and fluorine equatorial, that's going to be less than 90. Same thing here, fluorine axial to sulfur to fluorine equatorial. This angle is going to be less than 90. So if we add those together, the overall angle is 173.1. Again, don't need you to memorize that or anything like it, other than I do want you to know that lone pair forces these axial back, and it forces the equatorial ones closer together. And you go, why do I need to know that? Because we're going to be talking about molecular polarity. We've been talking about bond polarity and dipole moment of the bond. But when we start talking about molecular polarity, you must draw the proper structure. If you don't draw the structure correctly, you're going to choose the wrong answer. So it's really important that you draw a great picture of the structure in order to do well. So just like this one, there's a lone pair down here on bromines down in this area. Notice it forces the axial fluorines closer to the equatorial fluorine, and it forces it by 5.2 degrees there. 5.2 degrees on each one of these. 5.2, 5.2, 5.2, 5.2. And then the equatorial ones, the base of the square pyramid, they're not quite 90 degrees. They're 84.8. All due to that lone pair that we actually don't even see. When we clean this all up, we don't even see the lone pair. But we know it's there. How do we know it's there? Because you've done a Lewis structure. You've put the extra electrons on the central atom, and you would see that it's the classification for this would be AB5. Well, let me get a pen here. AB5. And that one's no good. AB. So this would be AB5E. So that's what it tells you. Oh, it's 6 things coming off. It's based on the octahedral electron domain geometry. But the molecular geometry would be square pyramidal, square pyramidal. Square base here, square base, and then the top of the peak here. All right. Let's see. All right, the geometry of a molecule with more than one center. Now this is really important. This is important in organic. It's important in chapter 11. So this is a molecule that has 2 central atoms. It's the carbon here. It's the oxygen here. So this is methanol. This group here is called methyl. All right, with the bond there. And then this makes it an alcohol, the OH group, off of a non-metal non-metal component of methyl called methyl. All right. So because we have 2 central atoms, we have to evaluate the geometry at both the carbon and the oxygen. So stop the video and classify, like AX and E, classify the carbon and the oxygen. So give me the classification and then tell me what the electron domain geometry is with respect to carbon and with respect to oxygen. And then what the molecular geometry is at the carbon central atom and the oxygen central atom. If you can do all of that, you're in great shape. If not, then pay attention. I'm going to tell you how to do it, and we'll work from there. But stop the video, and again, determine the classifications for both the carbon and oxygen, and then determine the electron domain and the molecular geometry for this molecule. All right. So when we look at this, you would look at the carbon. You say, oh, there's 4 bonds coming off of it, so it's AX4. So AX4 for the carbon. 4 bonding groups coming off. Then you look at the oxygen. You go, oh, well, there's 2 bonding groups, so that's AX2. And then you have 2 lone pairs here, so that makes it E2. So that's the start. Tell me what the classifications are on your central atoms. Now, when you see AX4, you go, well, this is going to have the same electron domain geometry and molecular geometry. Because if it's all bonding groups and no non-bonding groups, these 2 are going to be the same. So the question is, how do you keep 4 things away from each other as far as possible? You use the geometry called tetrahedral. So here it is. That's that one. That one's coming back out of the board. This one's going back through the board, and then this is solid. There's my tetrahedral right there. Here's one side of it, like that. Here's the other side. There's a side behind it, goes up through here and down through there, and then the one underneath. Okay, so now we're going to evaluate the oxygen. So this is an AX4, it's AX2E2. It's still four things coming off. So four things are coming off. The electron domain geometry is still tetrahedral. All right, so four things, whether it's bonding pairs or non-bonding pairs, there's four things coming off of the oxygen, two lone pair, two bonding pair. So the total is four, and it's tetrahedral. Now, there's a pair, let's see how long I do. There's a pair here that you don't see, and there's a pair back here that you don't see. I'll make it dashed. So that's why the molecular geometry is what you see with just the bonding pairs, which is this, and you would say it's bent. Bent. Because we're going here, and then we're bending down to here, and it's due to that. It's due to those lone pairs of electrons here and here. All right? So let's talk about what you just did here. You took a molecule called methanol. You do the you do the Lewis structure, and you realize, no, you got two centers. You got a carbon here and an oxygen here, and you have to evaluate both for their electron domain geometry and molecular geometry. And you go, so what? Well, based off what you write here or here, the electron domain geometry and molecular geometry are the same tetrahedral, then you're able to draw this. You're able to show the three-dimensional characteristic. And then this one you said it's bent, so that's why we just see this being bent right here. So that's the power of VSEPR, is you can take a Lewis structure. Well, let's put it all together. The power of Lewis structures is that you can take a chemical formula and draw a Lewis structure. And then the power of VSEPR theory, valence shell electron pair repulsion theory, is you can take this Lewis structure and actually come up with the three-dimensional geometry of the substance. I mean, it's just amazing it even works to me, but it works really well. All right, so let's have you do this one. Let's have you, it says determine the molecular geometry about each of the central atoms and determine the approximate value of each of the bond angles in the molecule. All right. I want you to do this one, but I just want to say you've got three central atoms on this one. So you're going to have to evaluate three atoms. All right. So stop and do the classifications for this one, for here, and for here. Once you get the classification, determine the electron domain geometry. That's the important one. That gives you the three-dimensional structure. And then ultimately determine the molecular geometry. Once you get the molecular geometry, you got a nice picture of it, then you can start talking about bond angles. All right? So it says, which, if any, of the bond angles would you expect to be smaller than the ideal values? All right? Well, we know the name of the game here is when you got lone pairs, that causes some distortion here. Okay, so stop and then we'll pick up from there. All right, welcome back. So first thing you do is you look at that carbon. You go, oh yeah, I've seen this a number of times. It's AX4. It's four bonding pairs. 1, 2, 3, 4. They're all bonding pairs, and the molecular geometry and the electron domain geometry are the same, and it's tetrahedral. So there it is. Here's your tetrahedral right here. That one's coming out at you. That one's going back behind the board, and this one's going back behind the board, and this one's on the same plane. So there it is. Tetrahedral. The angle of a pure tetrahedral, approximately 109.5. All All right, that's what you need to know. Then we look at this carbon here. And this carbon, the classification is AX3. Why is it 3? Because there's a bonding group here. A double bond is one group, and then a single bond here. That's all that's coming off that carbon. It's AX3. So again, if it's all just X's, the electron domain geometry and the molecular geometry are the same, and that is trigonal planar, flat. Trigonal planar. So you say, what do you mean trigonal planar? Oh, look at this carbon right here. This oxygen and this oxygen here are all in the same plane. It's 120 degrees here, 120 degrees here, 120 degrees there. All right, that's 360. All right, next one. Let me clean up some of this. It's getting kind of crowded. Yeah, let's trace this off too. All right, so the next one, can I get a different color maybe? Or how about this and then change that to red? Is that going to work? Yeah. All right. Did I get the red? Yeah. So you look at this oxygen and you go, oh, well, that's AX2E2. Non-bonding, non-bonding. That's my E2. And then the X is this one and this one. All right. And so AX2E2, you go, oh, it's not going to have the same electron domain geometry and molecular geometry. So the electron domain, you look up here and you go, oh, it's 4 things coming off the central atom. Tetrahedral. And that's correct. It's 4 things coming off the central atom. The geometry is tetrahedral. Now, because it's AX2E2, the E part is it's invisible. So when we look at this part, right here it is. This is the carbon, that's the oxygen, and that's the hydrogen. You can see it's bent. The lone pairs are out here somewhere. But what you see is the molecular geometry is bent. If it's bent, you know that the angle between, it's 4 things. It's still 4 things. So what you would say here is the angle between the carbon, the oxygen, and the hydrogen is less than 109.5. And you go, why did you say that? Degrees. Because this is a tetrahedral electron domain geometry. You wouldn't say less than 120 because 120 would be something like this. AX2E or something. AX2E, yeah. But this is AX2E2. So the framework was tetrahedral. The molecular geometry is bent. There's 2 lone pairs they're not showing here that's bending this to making it less than 109.5. So that's a little trickier one. That's about as hard as they get. If you can do that problem, you're in pretty good shape. All right. So we're going to stop this video here because I know you've listened long enough. And like I said, you shouldn't listen to these videos for an hour. It's not really ideal. What you want to do is listen to about 20 minutes, read some, listen to some more. Or if you've read and you don't understand something, then watch the video. So we're going to stop it here, and I will make another video coming up to finish chapter 9.